Welcome students. So today I am going to discuss a topic that is mathematical modeling of fluid systems, and this reference book is also written here. So let me start with this particular topic. So actually this most versatile medium for transmitting signals and power is the fluids, that is liquids and gases. Okay. So here these liquids and gases have wide uses in industry. Liquids and gases can be distinguished basically by their relative incompressibilities and the fact that a liquid may have a free surface, whereas a gas does not have a free surface. A gas will fill up the vessels, okay, where it contains. So this generally we denote this fluid, this particular transmitting medium as the fluid, and there are different classifications in the fluids. One is pneumatic, another is hydraulic. Okay. So these pneumatic systems means that will in that pneumatic system this transmitting medium is air or gas, and in hydraulic systems this transmitted medium is oil, that is in engineering system. Okay, engineering system applicable to automation industries. So this liquid level system which you can see here, that is actually applicable for process industries. In this case liquid level systems, this is actually having different applications in process industries. So this I am going to discuss first. So in this particular figure you can see that there is a tank and this liquid spouts through the tank and via this load valve which offers some resistance R, and this particular tank is having some capacitance. Capacitance is indicated by this capital C here. Here this is the capacitance C, this is the resistance R. This capacitance, resistance are defined to will be defined after some point of time because that will require to describe the dynamic characteristics of this liquid level system. You can see this is the control valve through which this is actually user controlled. So we can control this particular valve to change the inflow rate of the fluid. Okay. Now this as you must have wondering that this type of flow is basically having two types. One is laminar, another is turbulent. So let us say that is laminar flow, another is turbulent flow. You are familiar with these two terms. This laminar flow, that means this Reynolds number, if the Reynolds number of the fluid is more than if the Reynolds number is less than 2000, then it is a laminar flow, and if the Reynolds number is greater than 3000, then it is turbulent flow. This Reynolds number is non-dimensional flow, and this laminar flow is basically linear type of flow, and in between 2000 to 3000, if the Reynolds number is between 2000 to 3000, that indicates this transient zone. So laminar is in the laminar flow, this fluid flow will be in streamlines. So that is actually describable by linear differential equation, streamline flow, and that is described by can be described by linear differential equation. Whereas in case of turbulent flow, this flow cannot be described by linear differential equation. In this turbulent flow, this flow is nonlinear, and this nonlinear differential, this is actually nonlinear problem. So, but in this as I have told in earlier classes that any nonlinear flow system can be, any nonlinear systems can be linearized about the operating point. If the variables do not vary much around the operating point, if the variables will reside in the close vicinity of the, in the close neighborhood of the operating point, then the system can be linearized. So, in this case of turbulent flow, although this flow is nonlinear, it is well described by the nonlinear differential equation, still you will this linearized. So, whether the system is linearized or linear, that is actually our point of focus. If the system is non-linear, that is turbulent flow, then it should be linearized. In this particular system, basically this flow is turbulent because some kind of resistance is offered by the load valve, but still we are going to linearize this model before treating this particular control analysis. Okay. Now, in this particular system, you can notice that there is Q bar. What is Q bar? Q bar is the steady state flow, and Qi is the small variation of this over this steady state flow. This variation should be very small. Similarly, this Q, this is the output. If there is no variation in the steady state in the steady state condition, this Q will be input and same will be output Q. So, H will remain be fixed. This H bar, Q bar, those are not changing with time. So, those are steady state value. Now, if you give some small perturbation, that means if this Qi is given, then this Qo, this H will be increased, H will also vary, the height of the water level will also vary, and Qi will, Qo, that is the output from the tank, through this particular load valve will also increase by a certain amount. Okay. Now, before we proceed, we need to discuss this capacitance and resistance. We need to define what is resistance, what is capacitance. So, let me erase this. Okay. See, resistance R, resistance is R is defined as change in level difference, that is change in level difference difference in SI unit, it should be in meter, divided by change in flow rate. So, in SI unit it should be meter cube per second, volume flow rate I am talking about. Okay. So, it is actually analogous to our this earlier understanding related to electrical circuit. In electrical circuit, what is happening? This R equal to V by I, that is in case of electrical circuit. So, this V is the potential difference, here level difference is the analogous with this potential difference, and change in flow rate, here I is also current, that is also flow of charge, flow rate of this charge, here it is flow rate. So, it is closely analogous with this electrical resistance as well as mechanical counterpart. So, this is the definition of resistance. Now, at this particular restriction, if you look at this particular restriction, you can say that this Q, this flow rate Q is proportional to this height, this level of the water. Let us say this is the water level in this tank. So, that means Q equal to some constant of proportionality into H. So, this if you consider this linear resistance, this linearized system we are considering, although it is turbulent system, but we have linearized about the operating point. So, linear resistance is dH dq, it is change in level by change in flow rate. So, dH by dq, and in this case q equal to kh. So, dH by dq is equal to 1 by k, where k is the coefficient, flow coefficient. Okay. So, now in case of turbulent flow, if the flow through the restriction is turbulent, then you can write that q equal to, then you can write q equal to, if the flow is turbulent, then this q will vary with under root h. You must have seen in case of orifice flow. So, this multiplied by some coefficient kh. So, in this case dH dq, for this is for turbulent flow. So, dH dq is equal to k divided by 2 root h. Okay. So, actually this is one, there is one step jump. You can write that dq dh equal to this k into half into h to the power minus half. So, that means this is k divided by 2 root h. dq dh is equal to k half this one. So, this can be reduced like this. K by 2 root h. So, now RT equal to, this L stands for laminar, T stands for turbulent. So, RT equal to dH dq, that means 2 root h divided by k. So, that is equal to, so I am writing once again here, RT equal to 2 root h divided by k. So, that means 2 root h, and k is equal to, from this particular relation, k equal to q divided by under root h. Now, replace k in this particular equation. So, q divided by under root h. So, this is equal to 2h by q. Okay. So, now you notice that this RT RL equal to dH dq and RT equal to 2h by k. So, this this equal to this R L equal to dH dq 1 by k. Now, 1 by k equal to what? From this particular relation, you can see this k equal to q by h. So, 1 by k means h by q, that is for R L. and for RT 2H by Q. So, this is actually double of this RL. This approximation is double at this RL. Now, this generally this K, this coefficient cannot be obtained easily, because this will require some experimentation. So, what we will do, we can find out this Q from the graph of flow versus head. So, let me show you in the let us come to the next slide. Sorry. So, you can see here this head versus flow rate. This is head, means this is your H, and flow rate means Q. You have to draw the graph of this head versus flow rate, and from this graph, this is the plot of the graph. You can see this is clearly non-linear. This is because of this turbulent in this flow, and from this graph you can see this P is the operating point. So, at this operating point, if you are operating point is this one, and you have to work on this close neighborhood of this operating point, that means there is some small variation of this H with respect to Q. This variation is H and this is Q. Then this laminar approximation is valid. That means RL equal to H by Q. And if you consider this turbulency, then you can see this basically H by Q equal to what? This is the H, this is by Q. That means this particular slope. So, tan inverse, this you can see this theta equal to tan theta equal to this H by Q. So, this theta equal to tan inverse. So, this H by Q basically RL equal to H by Q, that means tan theta. If you consider this angle as the theta, so that means theta equal to this, we write here theta equal to tan inverse RL. So, the tan inverse RL, this is the theta. Okay. So, that is actually for laminar consideration. You see this is here RL tan inverse RL. So, now if you consider this, if you draw this tangent at this particular point, then tangent will meet, will intersect this y axis at this minus h coordinate. So, this height, this particular angle is how much? This particular angle is this total height divided by this total height is 2h and this length is q. So, then this RT equal to 2h by q, that means this is the slope, this tan of this theta. So, this theta equal to tan inverse RT. So, generally this type of plot is drawn with the help of experimental data or test data, and then from this particular operating point you draw a slope. So, at this particular operating point, what is the resistance offered by this particular load valve, that can be obtained by measuring the slope at this operating point. If you measure the slope at this operating point, then this resistance will be, this angle will be different, accordingly resistance will be different. So, this resistance will change depending upon the operating point. Okay. So, that is actually the concept of resistance. Next, let us consider the concept of capacitance. So, first I am going to discuss this capacitance. Okay. So, capacitance is this one, capacitance. This capacitance C is defined as change in liquid stored divided by change in head. So, change in liquid stored, that means it is in meter cube, and that means volume change in liquid stored, and change in head, it is in meter in SI unit, that means this unit is meter square. So, capacitance is meter square, whereas capacity is meter cube. Capacity of this particular tank is in meter cube and capacitance is meter square. Unit of capacitance is meter square. Okay. So, this is again analogous with the electrical system. In the electrical system, you must have seen this particular equation, that is this electric E equal to 1 by C integration I dt, that means this C equal to this integration I dt means charge divided by voltage. This is actually voltage, charge divided by voltage. So, in this case charge means this is the charge stored, that is same as the liquid stored, and voltage means change in head, that is the change in head, that is the potential head. So, you will find the clear analogous with the electrical system in this case also. So, now this C dH, from this particular definition you can write this C dH equal to, that means dH is the change in the head, equal to this QI minus QO. QI is the inflow rate, QO is the outflow rate. So, in time dt, this dH in the dH signifies that in infinitesimal time dt, what is the change in this H. So, in this infinitesimal time, this is the change in the outflow. This CdH means what? CdH is change of the liquid stored, and that is nothing but Qi minus Q0 dt. So, Qi minus Q0 is the change in flow rate, that is inflow rate is greater than the outflow rate, and this net if the inflow rate is greater than outflow rate, this change in height will be positive. So, that is happening in time dt. So, this equation is obtained from this particular basic definition. So, now Q0 equal to QO, that is output flow rate, outflow rate is equal to H by R, considering linearized system. This R is considering this R is R linear. So, now this C dH dt, from this equation 1 you write this C dH dt is equal to Qi minus H by R. I have substituted this QO by H by R. Okay. So, C dH, in the next step, C dH dt plus H by R equal to Qi. Now, multiplying R throughout, RC dH dt plus H equal to R Qi. So, if you take Laplace transform of this particular equation, then it is RCS Hs plus Hs. So, RCS plus 1 into Hs equal to RQIS. So, that means Hs by QIS equal to R by RCS plus 1. Now, note this RC is basically time constant. So, RC, if you do the dimensional analysis, you will find this RC will have the same unit of time, that is second. So, this is actually time constant, which was explained in the earlier classes. So, now the Hs is taken at the output, and Qi, that is the, because of this input Qi, this Qi is the input, in this case Qi is the input and H is the output. Then the corresponding transfer function is Hs. This capital H here represents this Laplace transform of small h, capital Qi represents the Laplace transform of small qi. Okay, so this is the system transfer function. If you consider Qi as the input and H is the output, instead of H as the output, you can consider no, H is not the output. We have considered Qo as the output. So that means in that case you have to find out QoS, your Laplace transform is QoS by QIS. So that will be what? So this see from this particular equation, if you consider QoS equal to 1 by R Hs, that means this Hs equal to so here QIS equal to Hs by R. So this is the relationship. Okay, let me write down here Hs equal to RQOS. So you have to find out this one. Now from here you can write, replace Hs by RQOS by QIS equal to R by RCS plus 1. So this R will be cancelled out. So QOS by QIS equal to 1 by RCS plus 1. So this is the transfer function, considering this as the output and this as the input. And instead of that, if you consider this as the output and this as the input, then this will be your transfer function. So this is in case of single tank system, when liquid spouts through the single tank, then this is the corresponding equations. Now let us consider in the next example that is for connected tank system. This is two tanks are interconnected. Between them there is some resistance R1 and another resistance, this is connected to the consumer, that is R2. So this type of systems, this is called two tank system. Similarly, there are three tank systems. This type of systems are generally used in process industries, where different tanks, different storage systems are placed one after another, particularly in case of these different process industries such as these petroleum industries. There are many tanks, okay, that is actually offshore petroleum industries, you will find this type of applications. And there are different process also. So let us now concentrate on this two tank system. So here you use these basic definitions which I have discussed earlier, that is, one is this Q bar, as earlier this bar, Q bar, H1 bar, H2 bar, these are actually steady state values of this inflow rate. This is the steady state height, this capital H2, all are steady state value, this bar, capital casing, and this small one is the small variation, that is the variation of this inflow is small q, variation of the height is height of the first tank, tank number 1 is H1, variation of H2, and the tank 2 is H2, similarly Q2. So this variation will occur because of the input q, small q. If you put this q, small q equal to 0, there will be no variation, this steady state will be maintained. Once you vary this capital Q, that is called the perturbation. The small perturbation will lead to this type of variations. So if that is the case, then you can write down this constitutive relations first using the basic definition, that is this potential head H1 minus H2, this difference in head divided by Q1. Consider this flow through this particular valve. So this is the resistance offered by this valve here, R1. So R1 equal to this potential difference, that is H1 minus H2, small h1 minus small h2. Actually this one, this small h1 you have to consider, this steady state value is not considered, because in the dynamic conditions there will be some variation of this potential head, that variation we have to take. So, that is the R1 equal to H1 minus H2 divided by Q1. Okay. So, another is from this second one, from this one, this is H2 divided by H2 minus 0, because reference line or data line is 0 head. So, H2 divided by H2 divided by Q2 equal to R2. Now, another is C1. What is C1? C1 into, you must have seen in this earlier case, this equation we have developed, C1 dH1 equal to Q minus Q1. C1 means this tank, capacitance of tank 1 into dt. This was explained in this earlier case. So, this is C1 dH1 dt equal to Q minus Q1. And similarly, in this, for the second tank, we can write C2 dH2 dt equal to Q1 minus Q2. Okay. So, now we have to draw the block diagram to solve this particular equation. So, this from this equation number 1, let us take this, this is your equation 1, equation 2, sorry. These 4 equations you can see, equation 2, equation 3 and equation 4. Now, you take Laplace transform of equation 1, that means H1 s minus H2 s by R1 equal to Q1 s. So, what is the corresponding block diagram? That is, there is one summing point, one plus, another minus. So, in the plus port there is H1s, in the minus H2s. So, this output is basically H1s minus H2s, that is going to be multiplied by 1 by R1, a gain value, and this output of this is Q1s. So, from this particular equation we have obtained this block diagram. So, next come to equation number 2. From this particular equation number 2, what is this? Let me now erase this equation 1. So, from equation 2, this Laplace transform is from equation 2, this let us say this C1s H1s equal to Qs minus Q1s. So, or you can write Qs minus Q1s, this multiplied by 1 by C1s equal to H1s. See, in this way this H1 is defined. So, what is the corresponding block diagram? So, again I am drawing this block diagram. this corresponds to equation 1. So, this I am drawing corresponding to equation 2. So, this is your Qs, this is your Q1s. Just follow this equation 2. This output is multiplied by 1 by Cs, C1s, and this output is H1s. This H1s S is basically these two are same, this is same H1s. So, this is from equation number 2. So, let us now erase equation number 2. Okay. Next come to equation number 3. This equation number 3 means this H2s equal to R2 into Q2s. That means H2s divided by R2 equal to Q2s. This is equation 3. So, we will consider this as equation 3, this Laplace transform of this original equation. So, what is the block diagram corresponding to this, that is H1s, H2s, this signal is multiplied by 1 by R2 and this output you will get Q2s. Okay, next consider equation 4. This is equal to C2s, H2s equal to Q1s minus Q2s. So, that means H2s equal to Q1s minus Q2s into 1 by C2s. So, let me now draw the block diagram corresponding to equation 4. So, this block diagram will be another summing point plus minus Q1s, this is your Q2s, this output is multiplied by 1 by C2s, this output is going to be H2s. So, this is from equation 4. Okay. So, Qs, Q1, this is from equation 1, this is from equation 2, and where is from equation 3? I think that is deleted. So, I am again once again drawing, this is actually simplest part. One by R2 is Q2s. So, this is from equation 3. So, 1, 2, 3, 4, you have got 3 block diagrams. Now, you can notice the interconnectivity. See, H1 is used here, this H1 is output here, H1 is input, H1 is output. In this case, H2 is input, in this case H2 is output. So, this output should be connected to here. So, again H2 is input here, then this actually H2 is input here, that is multiplied by 1 by R2 to find out Q2. Okay, so then Q1 minus Q1s minus Q2s, this is actually Q1 Q2. So, how you will find out Q2? From this H2 you have to multiply 1 by R2, then Q2. This Q2 is the output here, Q2 is the input here. So, these two will be connected. Similarly, Q1, this Q1 is here and here Q1 is the input and here Q1 is the output. So, these two input outputs are connected. So, after connecting all these particular signals, you will get this type of this type of structure, you notice this first one, this just I am drawing. Okay, let me now start this drawing first, so that you will understand this QS. Let us start from QS. This is your QS. Let me remove first, because it is of no use. So, let us start from here. This QS plus minus, this is QS and this is Q1S. I am not writing Q1 right now. This output is 1 by C1S, then this is connected with H1S. Okay, this H1S is input here. So, you see this H1 is basically output and this H1 is input. So, now pick up this particular block. This H1 is going to input here. This is your minus. Then this is going to let us put the minus sign here. So, actually there is no specific reason, you can put minus sign anywhere, but to make it very looking good, you have to put it here. So, this is your H1 is the output, H2 is the input here, that is coming to the negative terminal. Then this is multiplied with 1 by R1. Then it is becoming Q1S. This Q1S is here, Q1S. So, now pick up this equation 4. So, Q1S is going to this plus minus, then output is 1 by C2S, then this is your H2S. So, see this H2S is the input here. So, H1S minus H2S. So, this H2S is connected here. Okay. Now, this is actually QS minus Q1S. This Q1S you are getting here. So, this Q1S is this Q1S will be connected to here. This is your Q1S. So, in this way you have to proceed. So, after proceeding you will find this is the final block diagram. So, after using the technique of block diagram reduction, you will be able to find out this particular block diagram. This is actually these two inner loops you can form. These two inner loops is basically this is your negative feedback system, this is one inner loop negative feedback system. So, for this negative feedback system you can say that this is your plus minus. So, this is 1 by R1 C1S Q1S. So, this can be equivalent to this G by 1 plus GH. Okay, that formula I am going to apply. So, that is G1 means 1 by R1 C1S, G by 1 plus GH 1 by R1 C1S, that means 1 by R1 C1S plus 1. So, that is given here. Similarly, 1 by for this particular branch you will get 1 by R2 C2S plus 1, and this is as usual R2 C1S. Now, in this case these two will be multiplied because these two gains are in cascade. So, this multiplication is 1 by this QS, and here you are getting this 1 by R1 C1S plus 1 into R2 C2S plus 1 Q2S R2 C1S, this will be going to here. So, again this is your H, this is your G. So, if you reduce it, then it will be again this QS our input, Q2 output, and in between you will get G by 1 plus GI using this basic formula. So, you will get this type of complex transfer function. You must notice that this transfer function is not the mere multiplication of these two gains, that is two tanks are basically connected. You can come to here, see here two tanks are connected like this. What is the transfer function of this first term? First tank is 1 by R1 C1S plus 1, that is the transfer function of this first tank, that is equal to QIS Q1S by QS. And what is the transfer function of the second tank? That is Q2S by Q1S, 1 by R2 C2S plus 1. Now, if you just multiply these two, then it is Q1S by QS into Q2S by Q1S. So, Q1S cancelled out. So, overall transfer function is 1 by R1 C1S plus 1 into R2 C2S plus 1. So, intuitively it may look like this, but it is not actually happening because of the intermediate loading. Because I have told you in case of discussing LRC circuits that if these two LRC circuits are connected for this effect of due to this effect of interconnection, these two transfer function cannot be merely multiplied. There will be some intermediate loading. In this case also this intermediate loading is coming. So, that is why this transfer function, this is actually system's overall transfer function, but this is not correct. This is not correct. Whereas this is correct. You can see this is not the multiplication of these two things. See 1 plus R1 C1S into 1 plus R2 C2S means what? That is R1 C1 R2 C2S square plus R1 C1 plus R2 C2 into S plus 1. Okay. Now, everything is okay, but there is one extra term. This is the extra term R2 C1. This R2 C1, this extra term is due to the intermediate loading. This R2 is coming from second tank. C1 is coming from first tank capacitance. So, that is one intermediate effect. Due to that, this term is coming. So, it is not merely multiplication of these two transfer functions. So, that is the point to be noted. Okay. So, that is all regarding liquid level system that is used in case of process industries. It can be sugarcane industries, it can be petrochemical industries like that. So, any process industries, this type of liquid level system is having some relevance. So, let us stop here. Thank you for your attention.